Hi there, welcome back. Today we're going to be doing something a little bit different. This lecture is actually inspired by a trip my wife and I took a few years ago to Snoqualmie Falls in Washington. It's gorgeous, it's amazing, big huge waterfall, really picturesque spot. And let me show you the video of what this waterfall looks like. And it looks different in different parts of the year, but this is the one I want to take a look at. Very cool waterfall. And it loses a little something in not standing there in front of it, but you know, water spraying everywhere, and it's pretty and wet and whatever. The question I had as I was standing here watching this thing is, what would happen if you were standing underneath it? Could you actually stand underneath this waterfall? It's 282 feet high and survive? Or would the weight of the water pressing down on you crush you? And because I've stood underneath a few waterfalls, but nothing ever like this. So that's what we're going to look at today. So a couple things to consider about this waterfall. First of all, 282 feet is actually an 82 meter drop, but we're just gonna go to one sig fig here. And just kind of eyeballing where you would stand, it'd probably be in this area right here. I figured that was about a 30 meter diameter impact zone based on the height. If this is 80, this is about 30 meters in diameter. A couple more things. I looked on the U.S. Geological Survey website, and they say that the average flow rate is about 500 cubic feet per second over the entire fall. So if you think about that, that's 500 cubic feet of water, or maybe if this is 250 feet from here to here, it's 250 feet linearly by 2 feet high by 1 foot deep of water coming over the falls. And one other bit of information I just kind of guesstimated is this is a picture of what you might look like from above looking up into the water stream as it's coming down on you. And I figured you were about 1 foot deep from back to chest and about 2 feet wide from shoulder to shoulder. Now again, this is all just an approximation, and you know, the numbers might vary depending on the position you're in. But once again, if you stood underneath the falls, how much force would you feel? And I thought about this for a long time, and I tried to come up with some sort of an analysis technique that would explain, or that could come up with a prediction of what that force would be. And I realized this was really just either you could consider it an impulse momentum or a Newton's second law question. And so here we go. We're gonna see if we can figure it out. So what I realized, this was one of those cases where force equals velocity times a mass flow rate, a dm over dt. What dm over dt means is that there's a mass coming, a certain mass hitting per certain unit of time. So what would the units of that be? It would be kilograms per second. And what is the thing that's hitting you? Well, it's actually stuff. It's water. And it's constantly hitting you at a certain number of kilograms per second. So all you really have to do to figure this out is figure out the speed of the water as it hits you and multiply it by the mass flow rate, or the kilograms per second of the water as it hits you, and that'll give you a force in newtons. All right, so here we go. First thing we want to figure out is what would the speed of the water at the bottom of the waterfall be? Considering it's a vertical drop of about 80 meters and the acceleration due to gravity is 10 meters per second squared down. Remember, this is just to one sig fig. Of course, our initial vertical velocity is 0. How fast is the water going at the bottom? What I want to do here is I'm going to stop the video, have you stop the video, and do the calculation on your own, however you see fit. You can use kinematics or you can use conservation of energy, doesn't really matter. Come up with the speed of the water as it hits the person at the bottom. Do that now. And pause the video. Alright, hopefully you came up with a number. The number that I come up with is 40 meters per second. Alright, that's how fast the water's going at the bottom. So now that we've figured out the speed at the bottom, the next step... Alright, now that we've figured out the speed at the bottom, the next step is to figure out the mass flow rate onto the person. We know the volume flow rate of the whole falls is about 500 cubic feet per second. That's this 500 feet cubed per second. Of course, this is a physics class, so we're going to operate in meters rather than feet. And that actually does make our numbers come out. So one of the things we're going to have you do is I'm going to have it pause and figure out how many cubic meters per second are coming over the falls. Next thing you're going to figure out is that since we know that the density of the water is 1,000 kilograms per meter cubed, the mass flow rate over the entire falls must be, okay, and you're going to figure that one out. Finally, once you've got that figured out, since the water is landing in a 30-meter diameter area, it's a big, huge area, but the person is only a small little piece of only 2 square feet of that, the person receives only about 3,500th of the entire flow. So the next thing you're going to figure out is the flow rate in kilograms per second hitting the person. So take a few minutes and do that now. And you don't be afraid if you need to use Google to convert some units, that's fine. All right, take a few seconds, do that now. Go ahead and stop the video. Alright, the first number I come up with is the volume flow rate of the over the whole falls. That 500 cubic feet per second turns into only 14 cubic meters per second, but that's actually quite a bit of water. If you think of how big 14 cubic meters would be, and that's all coming over every second. Also, if you have 14 cubic meters and each cubic meter is 1,000 kilograms, that is 14,000 kilograms per second. That's a huge number. All right, that's on the order of a large truck every second, like a semi-tractor trailer type truck. That's full, not an empty one. All right, lastly, since the water is landing and only a small chunk of the water actually hits the person, we would divide that 14,000 by 3,500, and I come up with about 4 kilograms per second hitting the person. 4 kilograms a second. That means about a gallon per second. And if that doesn't sound like that much, well, it's quite a bit more than your traditional garden hose. So just think of every second you're getting smacked in the face with a gallon of milk. All right, so that's what it would feel like. All right, we're going to put all of that together on the next slide. So here we go. Now, the force of the water on the person. We know that the force would just be the velocity times the mass flow rate. So go ahead and calculate the force in newtons, and then once you're done, convert that into force in pounds, and then we'll talk about what you get. Go ahead and pause the video now. All right, I get about 160 newtons of force of water hitting you. If you do a little bit of conversion, that comes out to be about 35 pounds. Now, if you had 35 pounds of water hitting you, would you survive? Probably. Would you be able to stand up? Probably, depends on your footing. But what if you did lose your footing? What would happen to your cross-sectional area? What would happen if, you got a little slip and all of a sudden you're sitting sideways? Now how many pounds of force is it? Oh, it might double or triple. So now you're talking 70 or maybe over 100 pounds of force. So you can see why standing under a waterfall is a precarious predicament to be in. And not only that, but that 35 pounds of force was, well, you made a lot of assumptions going into that. One of the big assumptions that you made was that all the water was hitting uniformly at the same speed, all in this big, huge 30-meter diameter area. Now, the reality of the situation is it probably doesn't work that way. If you go out towards the edge, you might only be getting a little bit of spray. But if you go down to the very center, you might be having big, huge gushes of water. So 35 pounds on average might translate into several hundred pounds instantaneously at one particular spot. And if that happens, I pretty much guarantee you're not going to be able to keep your feet. Moreover, if you think about what's at the bottom of the waterfall, it isn't probably rocks, it's probably just a big pool of water. So what's really going to happen is that multiple hundreds of pounds smacking down on top of you is going to plunge you way down deep into that pool of water. And what ends up happening is you end up recirculating and recirculating and recirculating, going under and under and under and under again. And so, in the end, being under this waterfall is probably a pretty bad idea, because if you do, you're going to get stuck, and once you get stuck, you're not going to be able to breathe, assuming you don't hit your head on the rock as you get churned around, and you're probably not going to make it. So, anyway, I hope this was illuminating to you. You could do the same with any waterfall. All you have to do is look up on the U.S. Geological Survey, figure out what the flow rate is, figure out how high the waterfall is, and you could kind of make a ballpark judgment as to whether or not it would be safe to stand underneath it. Or you could just look at the waterfall and use common sense. Hopefully you learned a little bit from this, and I will see you soon. Thanks.